Good afternoon, I am Mr. Ish. We are looking here at an interesting, good video. Often neglected proof is the title of this video. If you think back to your integration questions or your integration subjects, the topics, especially when you've been looking at, we can talk about areas and volumes, derivations. You've always seen this specific integral interval property come into play for an even function. You know, an even function has the property f of x is always equal to f of minus x. Anyhow, when you've seen an interval such as minus a to a f of x dx, you've always had the luxury of bringing in this specific 2, and you can do from 0 to a and f of x dx. That allows you to eliminate the minus a, and you're looking at a shorter interval, which makes the whole computation easy, and it's an excellent shortcut. What we're saying is, if you have an even function such as this from minus a to a, and you were to look at the area below the curve, you could do a shortcut technique such that you're only looking at from 0 to a, and you're just computing this area and you multiply it by 2, because this area happens to be identical to that because it's symmetric about the y-axis. This right here is often studied and we are very well aware of it. What we want to look at in this video is the odd function and how that relates to intervals, because that is frequently neglected and the proof of it is frequently never taught. So we will look at that in this video. For an odd function, we always see this come into play. You have minus f of x is equal to f of minus x, because this function, whatever it might be, ends up being symmetric around the origin. Very simply a graphic representation from minus a to a, we're looking at the area below the curve from 0 to a, but an area above the curve from minus a to 0. When you do the integral procedure for this, f of x dx, you know you're looking at it from minus a to a. For whatever reason, we know what the reason is, but let's just say for whatever reason it ends up zeroing out. And the reason why that happens, well, intuitively you're looking at a minus area here and a positive area here. When you net them through, you end up getting a 0. But we want to be able to prove why this is the case. It is, especially when you are looking at an interval from minus a to a. What's an example of an interval minus a to a? It's like minus 5 to 5. You have the same numerical number in terms of a, but one is minus, one is positive. It's not going to apply for situations where you're looking at minus 5 to 10, because these are not identical numbers here in terms of digits. They're not identical digits. They have to be identical digits. In that instance, for this odd function, you'll always end up getting the 0. So let's prove this to be the case. The net area being 0 for these instances in terms of definite integration or definite intervals is an excellent property to prove, because we don't frequently see it done in our class. We will do it here. And how will the procedure start? It will be like this. You have a minus sitting outside, and we're proving this, of course, and we are looking at everything here from an interval minus a to a, because that is what the odd function, this property where the area ends up being equal to 0, is what it's all about. From that interval, we have this minus and we have to integrate this. You can do your interval minus a to a. You have an f of x dx. That's the left side of the equal sign. Let's come to the right side of the equal sign. We have a minus a to a, right? We have an f of minus x dx. What we see here differently here compared to here is we have an f of x, but we have a f of minus x. This we can do something with. If u is equal to minus x, then du is equal to minus dx, and dx is equal to minus du. But we're dealing here with definite intervals, so these intervals will change. u1 is equal to this minus, being everything affected in terms of that, minus minus a, which makes it positive a. u2, you feed this upper value right in here, you get a minus a. This here becomes from a lower interval now, which becomes a positive a, and an upper interval, which becomes a minus a. You have a f of u du, but I haven't forgotten about this minus right here, this minus. We can bring that right out here. Now let's come back to this side of the equal sign. We can open this up. We have this a minus a f of x dx. What we can do now over here, very simply, is do the definite integration in this part. You know you're going to do the upper limit, the lower limit, and the difference of the two, and that's exactly what I'm doing, f of minus a. When you do the definite integration, the dx and the integral sign go away, because now you fed the upper and the lower interval into your antiderivative. Let's come right over here. You don't need to do anything here special, but you can, but I want, because when you're doing proofs, you want to ideally do them in an efficient and a less time consuming manner. We have this minus sitting out. Let's create a parentheses, and now we do your upper and your lower intervals being fed into here. We'll get f of minus a minus f of a, and we can close that up. Everything you see over here, nothing is out of the ordinary so far, and nothing will be, because this is an often neglected proof, but it's easy. Open this up, you'll have minus f of a, and you'll have a plus f of minus a. Here you'll have a minus f of minus a. Here you'll have a plus f of a. Bring the like terms together. Here's a like term, here's a like term, because they have a minus a in terms of their input. These are like terms because they have a positive a in terms of input. Let's take the positive a's on this side, the minus a onto the other side. We'll have a minus f of a, and then a minus f of a. Here we'll have a minus f of minus a, and a minus f of minus a. You gotta just do nothing more than combine the terms. Here we're getting a minus 2 f of a. Here we're getting a minus 2 f of minus a. You see all of that. The minus 2's can cancel out, because you could take it on the other side. It'll be minus 2 divided by minus 2 will be 1. You get f of a is equal to f of minus a. Take this onto the other side. You have f of a minus f of minus a. When you take this on the other side, what do you get on the other side? You get a 0, and there it is. That's why the net effect of that over the interval minus a to a, which I had written previously, for an odd function is always equal to 0. And look, how can you even get this very simply, just from no other way other than a simple integral minus a to a f of x dx, where this happens to be an odd function, symmetric about the origin. When you do the definite integration procedure, this is exactly what you get in terms of your antiderivative, with the upper and the lower limit fed in, equaling a 0, and there it is. Why? For an odd function in terms of net area, again I'll say it, the area is always equal to 0. And here's your proof, frequently never shown, but now you've seen it and you can remember this. Thank you for watching. Have a nice day.